so I've got a part sitting here on a machine tool. Let me just get the machine tool out of the way for a second. Let me just undraw the block. Okay, so for those of you that would joined on last month's webinar, you'll remember that I looked at sort of profile machining for doing deburring situations and that sort of thing. So if you look at this, I've got a sort of little deburring tool path that just runs around the edges of this mold just to take the sharp edges off. Okay, so if I bring the machine tool back and let's have a quick look at where we are here. This machine tool, I know, has got very limited travel in the y-axis. So if we look here, you can see now that that is the limits of my y-axis. So I'm not going to be able to reach around this part to sort of machine that. Okay, so we come to post this out or we come to run it on a machine tool, we'll get an error. So where can we use orientation vectors or power machining to get us out of this situation? So if we have a look at the toolpath itself, let's recalculate that. And let's have a look at the machine axis control tab, which is where the orientation vectors and the polar is kept. Now, for the majority of the time, when you're using a Trunnion type machine like this, you'll be using polar rather than orientation vectors. So we've got several different types available to us. We've got polar and orientation vectors. Okay, so this configuration machine tool, polar is the most common thing to use. So you need to tell it where the rotation centre is, and then majority of the time you'll be just using the centre of the machine tool, the centre of the part. You can offset it if you want to do some clever little polar tool paths locally, but to be fair, the vast majority of the time the rotation centre will just be whatever the centre of the part is. Okay, and in my example it's just the same as coordinate 1, which is on my global coordinate system, so I'm just going to leave that blank. The next thing it asks is which axis do you want to lock. So if we look down the front of the machine, if we can imagine we want to put the tool here on the part, okay, and we just want to rotate that C-axis and then use the X-axis to then deburr the part. Okay, so we don't want the Y-axis to move, so we would lock the Y-axis. Okay, so if we just calculate that toolpath, and you'll notice the toolpath looks exactly the same. Okay, so there's no difference between that and that. They're absolutely identical in every way. However, the toolpath contains rotary moves rather than just XY moves. So if we simulate that from the start, you can see that the C-axis now is rotated into a position ready for the tool to come into this position here. So if I slow that control speed down a little bit, okay, you can see now that we are just using the rotary of the machine tool deburr that part. Now this works with any strategy. It works with face milling or area clearance if you really want to do that, or anything, as long as it's a 3-axis strategy it will work. So corner finishing, constant Z, etc, etc, it will all work in exactly the same way. Excuse me. So that's locking the Y-axis. If we change that and lock the X-axis this time, calculate, simulate that from the beginning. Okay, you can see now that the tool is positioned fixed in the X and we're just allowing the Y-axis to move. So if we look down the top of the machine tool, so you can see just the Y-axis is moving and the C-axis. Okay. Now again, like I say, this works with any 3-axis strategy, so if you've got quite a deep pocket or quite a big pocket to rough out that's within very close limits of the machine tool, nothing stopping you doing an area clearance with this, nothing stopping you doing any sort of raster finishing or 3D offset finishing or anything like that. Okay. So that's a very quick insight into using polar. So let me just get rid of that project and just open another example up. So this time we're going to look at doing some drilling and maybe some profile machining around the outside and the inside of this part. So if we activate that toolpath there, and let's just simulate that from the start, and this is just straight out of the box drilling toolpath that just drills exactly as we used to expect to see, just X and Y and Z moves. Okay, so this time exactly the same toolpath. If we come down now to the machine axis control, you see I've got polar set. Now again, we can lock the X or the Y axis. So I'm going to lock the Y axis so the tool should come onto the center line. Okay, so we say calculate. So now, if we simulate this from the start, notice now that the tool remains exactly where it should be, and then just uses the rotary axis and then the Y axis to position the hole in the correct place. So let's turn this around. Let's this time lock the opposite axis. So if we come in, lock the X axis this time, say calculate, exactly the same as before. This time now we're working at the front of the machine. Okay. So let's go back into this and just point out one other little thing we can do. If we look at machine axis control, lock the Y axis this time, calculate, quick simulate from the beginning. Okay, so you can see the tool now is positioned out to the left. Okay, we can now, if we say we don't want it positioned out to the left for whatever bizarre reason, we want it positioned this side, we can say use complementary angle. Okay, so for any multi-axis move, there's always two solutions. I say this uses the secondary solution. So this time, if we calculate at the same time at the beginning, you'll notice now that it's fixed on the opposite side of the part. Okay. And it works exactly the same if we lock out the X or the Y. Now, I can't lock out the X-axis on this one. We use complementary angle because the tool would want to go to the back, and we haven't got the travel limit to do that. So it would use the only solution it can, and that would be at the front of the part. Okay, so let's have another look at another example. Simulate this from the start. This is just very simply just profiling around the outside of this stock. So I've deliberately made this so you can see we're hitting the machine tool there. Okay, so this part's too big for this machine tool, that tool's too big, and the stock, if I draw the block, it's all very close and all very sort of uncomfortable. Okay, so exactly the same as before. If we come down to our tool path and we go to our machine axis control, again I've set polar. I want to lock the X axis, so this will bring it down to the front for me, and say calculate. So if I look at that now, simulate that from the beginning. Okay, so you can see now that's nicely just sort of machining that part for us, and away we go. Okay. Now you'll notice that we've got this little warning here to say that we have not chosen polar links. Okay. Polar links, they're more geometrically optimized for polar mini-build connecting moves. If you're very close on your limits of your machine tool, you might still find that the connecting move might still run out of travel limits first. So what you want to do is you want to invoke a polar move from the very, very beginning, the very, very start point. Okay, so if we look at the beginning of that, if we play it a lot slower, okay, you can see it does that linear move, it follows it round. This is not a very good example, but you can have problems with it hitting the limits before it actually does that move. So what we tend to do is we want to have these polar links. Now if you hit this will take you straight to the page where you need to apply polar links, but they're just on the rapid moves page. And we just simply tick use polar links. Okay, so now if we calculate, you'll notice that the first move now is an arc move, is a sort of polar move on, if you like. So if we simulate that from the start, okay, it gives that first move down is a rotational move to its first point. Now I tend to not use block center safe anyway. So if this is me doing anything like this, I always tend to use first point. So if we come down here, so my start point would be first point safe, or just first point and give it a Z distance. And my end point I usually have last point safe as well. So it takes out that sort of dogleg move and leaves everything above the part ready to go. Okay, so we don't need to worry about that. So this comes from a tool change position that comes straight to that point anyway and follow it around. Okay, so we don't need to worry about that. So it can just go straight there. Okay, so you've not got any of these sort of little dogleg or rotational positional moves. That's just my personal choice to do. Okay, so let's just to show you that we can actually do other things other than just profile and drilling. To extend that home, we just select that surface, I create a new boundary from the model, just undraw that machine tool for a second, and select all those boundaries except those two, and delete those if I'm interested in them. And let's just create a quick toolpath in there. And let's go finishing. Let's create a constant Z finishing toolpath. And let's pick a new tool. Let's pick a tool that I've got in the tree there. Just pick that. Constant Z, spiral, thickness from 0, step down maps 2. Okay, so we've just got a quick spiral constant Z toolpath in there. My tool axis I've got set to polar. So I've bring our machine tool back and simulate that from the start. Okay, so if we play that now, you can see that we nice polar machine that in there for us. Okay, so that's really not a lot to polar machining. Once you understand locking the X or the Y and using polar links, that's going to cover 99.99% of everything that you're going to want to do. Okay, so let's move this on a little bit then. Let's have a look at using asymmetric heads. Let's look at a head-head type machine or a large gantry machine tool, and we'll look at using orientation vectors. Okay, so we'll pull this head-head control. And again, there's a tiny little bit more to this than polar machining, but not a great deal. Okay, so the first thing I want to explain as first example is how we can position the angle of this head. Okay, and a common one for this type of machine tool is if I just create a face milling toolpath and simulate that from the start. Give it a moment to just do its collision checking. You'll notice we're just face milling across there. Okay. Now, some of these machines, I mean, this is a relatively substantial machine tool, and some of these sort of head-head machine tools, they're not as substantial as this. Some of the lighter weight machine tools with router type configurations. We could have quite a heavy cut on there, and we're pushing against the actual axis of the machine tool there. So you're better off to push in this direction. So for whatever reason that you may have a restriction, you might not be able to machine in that direction. You might be able to machine, you might only be able to machine in that direction. So we want to be able to position that head. So we're pushing all the force of the machine tool at 90 degrees to where we are now. So if we come down to machine axis control, this time instead of using polar, we're going to use orientation vector. Okay, and we have several options available to us here, and you will only ever use these two options here. Okay, so we want to do a fixed direction. We want to fix the head of that machine. So we're going to say it's fixed, and now we can give it an angle. I'm going to leave it at 0 because I'm pretty sure. Yeah. Okay, so we need to position it 90 degrees out to that. So if I recycle that, my offset angle will say 90 degrees. Calculate. Okay, so again, it looks exactly the same until we come to simulate it and machine it. So you can see now we're machining with the head set at 90 degrees. So we're pushing all the force of those cutting forces in that direction rather than that direction. Okay. Fairly simplistic example, but fairly common at the same time. Okay, let's have a look at another example. Let's look at the settings. This is just a very simple surface machining toolpath just to machine this sphere here. Okay. Now this could be a pocket, it could be a slot, or whatever feature deep down in a mold tool or anywhere where there's an obstruction on the head and the part. Okay. So if we simulate that from the start, okay, you can see straight away we've got a collision. Let's accept that. Okay, so that's not ideal. Okay. So casting our mind back to the first example using facing against the axis, we now need to position that head 90 degrees out. So if we come into the settings, and we cycle that, machine axis control, we want to do an orientation vector. This time we want to do a fixed direction, offset angle, 90 degrees. Okay. So again, it looks exactly the same, no difference. Set it from the beginning, and away we go. Okay, so we've positioned the head 90 degrees out, so you can see we've got that nice clearance there. Okay, so that's fixed direction. If we come now, if we was to, if we look at the settings, if we come down to machine this one now, for example, calculate that one. Okay, start from the beginning. Now, because my orientation vector is still remembered from the previous toolpath, we need to just reset it. Okay, so if we come down, machine axis control, set angle 0, calculate. Simulate from the beginning, so we're just clear there. Okay, so that's really all there is to fix in the head in the correct orientation. Now, we're using 0 and 90 degrees. Obviously, you may have a part at a strange angle there. There's nothing stopping you going to the dynamic machine control, just twisting the head around, measuring the angle, and then putting the offset angle in there in exactly the same way. Okay, so that's fixed direction. Let's have a look at free. Let's say, for example, now we can't position that head 90 degrees or 0 to get all the way around that slot, because in this position it's clear. When it gets to this position, it'd start to collide and so on and so forth. Okay, so if we go into the settings, we calculate that toolpath just to highlight that. If we look at that, so you see we're clear there, but we're hitting there. Okay, so how do we get around this? Okay, so we can put a really long tool in, which is not ideal, or we can use one of the other options available to us. Okay, so this time, instead of using fixed direction, we want the orientation vector to always be the direction of travel. Okay, so whichever the contact, it's very hard to explain this, when we're the contact point of the tool on the part, and the direction of travel of the tool path, the head will stay perpendicular to that. So let me just calculate that, because this is easier to see than it is to explain. Let's position the tool path there. Okay, so we come across. Okay, I'm going to explain in a minute why it's doing that. So you can see now it's always staying perpendicular to its direction of travel. Okay. It's just telling me I've hit the limit to the rotor there. Okay. So again, so what we can do now, we can come in and we can put an offset angle of 90 degrees and calculate. Simulate from the beginning. This time we're 90 degrees to the direction of travel. So that's exactly what we want to see. Okay. Now, if we look at the beginning, you'll notice that we're still at 0 degrees at that position. Okay, if we come down, it's telling me we've collided, and then it gets to the tool path, and then it correctly positions itself. Okay, that's not actually an ideal situation. So what's going on there? Okay, so if we come into the tool path, come to display, and we can now draw the orientation vectors. Okay, so you can see these little red dashes on the tool path there, and here, and here. Okay, now these are showing where the head is in relationship to the travel of the machine tool. Now you'll notice that in this position here it's 90 degrees to it, and then it comes and then it changes. That's where we get the collision on the way down, and then it corrects itself on the bottom. So we've got orientation vectors going on in this first move. If you cast your mind back to what I was saying earlier, my personal choice for when I'm doing anything like this is always use first point to alleviate that first dogleg move or that first positional move. So if we come into the settings, if we recalculate this toolpath, come to my start point and use first point or first point safe, whichever you prefer, and calculate. Okay, you'll notice now that we've got the correct orientation all the way down. Okay, so if I say Control Q, it's in the correct position before we even do that move, so it'll stay correct. So we will manage to you can manage to get around that part without any errors or without it hitting the part. Okay. Okay, so that's the difference between fixed and direction of travel. Okay. Now again, very similar to polar. There's nothing stopping you if you've got an awkward pocket here that you need to area clear. There's nothing stopping you doing fixed direction. Or if you've got a circular pocket here, there's nothing stopping you doing direction of travel and letting you do an area clearance while it's following the direction of travel. Just be wary of the connecting moves between toolpaths, and again, just think about using start point rather than block center safe. Okay. Okay, so fixed direction of travel. Again, like I say with polar, there's really not a huge amount to it. So finally, I just want to look at drilling. Okay, so it works in a very similar vein to direction of travel, but the software tends to just get on with it and sort of figures it out itself. So if we just calculate those holes there, and if I simulate that from the beginning, okay, so that's, you notice now we've got a collision, okay, because the head is fixed. Okay. So exactly the same as before. If we come now to machine axis control and we say orientation vector, and we want it to be the direction of travel. Okay, don't think I need an offset on this. We'll see. Okay, simulate from the beginning. Yes, we do. Okay. So what it does is it looks at the direction it's got to travel to the next hole and then positions it angularly accordingly. Okay. So if we change that, if we put an offset angle of 90 degrees, simulate from the beginning, okay, you can see we can get around there quite nicely now. Okay. Well, that's all I'm going to cover on orientation vectors, and to be brutally honest, that's all there is to cover, because that's really, people tend to shy away from, they think they're quite complex, but once you understand that, what the difference between fixed direction of travel and entering the offset angle is, that covers 99% of everything you're likely to ever want to do. Okay, so I'm just going to recap very briefly about next month's webinar. So again, keep a lookout, webinar 7th of June, projection strategies, the first of 2 webinars. So we'll start with line, plane and point. Now I believe that my colleague Robin will be covering that one. I'll be at an exhibition, so I won't be around. And then the following webinar I'll be back on board, so I'll be looking at projection curve and surface. And like I said from earlier on, if there's anything you'd like to see, please let us know. And again, at the end of the seminar today, there'll be a short survey. If you could take a few moments to fill that out, and we'd really appreciate that. Okay, ladies and gents, that just leaves me to just thank you again for your time. We do appreciate it, and I hope to speak to you all again shortly. I bid you good day. Good day. Bye-bye.